of over 30 publications, as well as the New York Times bestseller Life 3.0. His most recent AI research focus is on mechanistic interpretability, as well as news bias detection with machine learning. And in May, he organized a Mechanistic Interpretability conference, which I attended. That's all I wanted to say, so let's get to the talk.
A little selfie with you all here. Such a pleasure to be here. Thank you so much for inviting me. So raise your hand if you are interested in AI safety. Ooh, this is I'm playing a home game tonight. Friendly audience. That's great. Raise your hand if you're affiliated with Harvard. So that's like an away game if you're from MIT. Anyone from MIT here? All right, I'm not alone if I get attacked. Great. Such a pleasure to be here to talk about provably safe systems, which I'm going to argue is the only path to controllable AGI. And I hope you'll find at the end of this, maybe despite a little bit of gloom here and there, this is actually an optimistic talk. So it's a very exciting time, of course, to talk about these things because there's been just such a remarkable pace of AI progress recently, right? For decades and decades and decades, the Turing test was like the holy grail, and when we got there, wow, here is Joshua Bengio, Nobel laureate equivalent in AI, saying that
we have basically reached the point where there are AI systems that can fool humans, meaning they can pass the Turing test.
And you can argue about whether he's right or not, but the fact that someone at the top of this field is saying we've passed the Turing test with things like speed-for, it already motivates the question, well, okay, how far will this go then? And a few years ago when I spoke at Harvard, I showed this plot, which is how I think about this question. The elevation here represents how difficult it is for AI to do different tasks, and the sea level represents what AI can do 3 years ago when I gave this talk. This is another just striking indication of how fast stuff has changed. I mean, look at things like the Vinograd test, totally underwater. Now, art, which was so far above, whoops, blub, 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 you know. And coding, so much cool stuff you can do with Copilot, etc. Reid Hoffman was all excited about how he wrote this last book entirely with GPT-4. So just a few years. So it's very interesting to talk about climate change and sea level rise and ask how far is this going to go, right? Is it going to end up pretty soon being like this? This is a definition of artificial general intelligence, that AI can do all these tasks at human level or better. And of course, if that happens, then that would include the job of AI development. 7 years ago, I switched my MIT research from physics to machine learning, so it would mean that I can also be replaced. And of course, that raises this controversial possibility that you might get an intelligence explosion where you can have AI development shift from happening kind of on the human R&D time scale of years to the machine time scale of months or weeks or days. And you might soon get AI recursively self-improved to the level where it's not limited by human ingenuity, but more like by the laws of physics, which is about 30 orders of magnitude higher than today, according to Seth Lloyd's estimates. So people love to argue about whether this is going to happen or not, but it's interesting how the perceptions have shifted in just 3 years. Again, 3 years ago, we still have my MIT colleague, whom I greatly respect, Rodney Brooks, saying it won't happen for centuries. Polls showed a lot of AI researchers saying it'll probably happen within decades. And now all of a sudden, you have Microsoft saying, it's already happening, folks. They have this paper out claiming sparks of artificial general intelligence that I think many of you have seen, right? And that has made some people worried. Here we have Jeff Hinton, for instance.
Are we close to the computers coming up with their own ideas for improving themselves?
Yes, we might be.
And then it could just go fast.
That's an issue, right? We have to think hard about how to control that.
Yeah, can we?
We don't know, we haven't been there yet, but we can try.
Okay, that seems kind of concerning.
Yes.
love how dead And then, not to be outdone, here's Sam Altman, the CEO of OpenAI, who gave us GPT-4.
And the bad case, and I think this is like important to say, is like lights out for all of us.
Lights out for all of us. We're all dead. And it's interesting that this isn't just some, some random dude who showed up at the colloquium. It's actually, you got the CEO of a company that's building this warning about it. And he's not the only one either, because then we had this extinction statement which came out in May, the shortest open letter I've ever seen, only one sentence, saying that mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks like pandemics and nukes. In other words, extinction is a thing. And it's so interesting we signed it. When was the last time that the actual leaders of an industry trying to build something warned that the thing they were trying to build could wipe us out? We got Sam Altman, we got Demis Hassabis, we got Daria Amodei, and also the leading researchers. So let me just try to summarize the whole intro I gave here with one slide of cat memes. And 3 years ago, we were kind of here. A lot of people were saying, well, artificial general intelligence, it's inevitable, it'll be fine. It's decades away. Last year, after ChatGPT came out and also DALL-E 2, people were like, it's inevitable, it'll be fine. And now, especially after the extinction statement, we're like, it's inevitable. There's still a lot of people who say it's going to be fine, although with a little bit less conviction, I have to say. They start giving probabilities, it'll probably be fine, and so on. And it reminds me a little bit of this cartoon, apologies for the partial plagiarism, some of you have seen it in its original form, but take transformer LMs and do some reinforcement learning with human feedback, some scalar oversight, and put in a lot more data, more parameters, more compute. And then it's going to be great. It'll be fine. Aligned superintelligence, cosmic utopia, no worries, And wouldn't it be nice to flesh out this stuff a little bit more in detail? Or is it just me? Who is completely convinced that we have a really solid guarantee right now that it is going to be fine? Not a lot of that. Okay.
Fine is a spectrum, right? We don't have to get the aligned utopia for things to be fine.
Yeah. But so it's great that people are trying all these things. I support all kinds of AI safety work. I don't want to mean to criticize anybody, but I would like us to be even more ambitious. And I want to talk a bit about this optimistic paper I posted a week ago together with Steve Omohandro, where we argue that there is actually a more ambitious path for actual provably safe systems. And I put a smiley face here to emphasize that I think this is actually hopeful. And the basic idea in just one sentence is that for high-risk situations, we should only allow provably safe systems. And then the rest of my talk is going to be explaining what the heck is a provably safe system. Is it hopeless to build them? I'm going to say no. Would they be useful even in the immediate term for the current harms and risks we're facing? I'm going to argue yes. And then I'll get nerdy and talk about how do you actually build them step by step. And finally, if anyone is interested in working with me on this, I'll tell you how you can do that. Mm-hmm.
This slide, as it is, could have been, is given in many different talks in computer science. In particular, I think Nada, over there were many talks in computer security, computer verification, say the same thing. Often in practice, people still don't have provably safe systems.
Exactly, and this is actually
what can we learn from these lessons?
A lot. So In cybersecurity, of course, it's so valuable if you can not just be fairly sure that something is safe, but actually prove it, especially when the stakes are high. And it's embarrassing in a way that we haven't already done more things like this. So for example, raise your hand if you have ever logged in using SSH. Yeah. Okay, raise your hand if you heard about the heartbleed bug. So it turns out, 2014, someone discovers that there's a bug in the SSH. Like, what? How could that have persisted for over a decade, you know? So pathetic, right? So wouldn't it be nice if you could have a formal proof that it's impossible to log in with SSH without having the right credentials? Or the bash bug, you know, who uses Linux and the bash shell, you know? Yeah, so the shell shock bug, also 2014, someone discovers there's a bug in bash, which can let other people get control of your system. Like, things like this, there are people out in cybersecurity who've been saying for a long time, formal verification should be good, it's great. In fact, there's been a really great DARPA project that produced the Cell4 verified operating system. But a piece of optimism I want to share with you here is this field which involves proving things, formal proofs about code, I believe is ripe for being revolutionized by AI. It has not really happened that much yet. I feel that it's 2014 all over again for this field. Before 2014 in machine vision, like classifying images, is this a cat or a dog? It had been in existence for a long time. You had all these different algorithms, benchmarks. Then machine learning just blew it all out of the water, right? That hasn't really happened yet for the field of formal theorem proving. I was talking last week with Rustam Leno, who's written this wonderful language called Daphne, which is the easiest to use tool for formal verification. In my opinion, it's a lot like Python, except you can actually, instead of just compiling, if you're lucky, it'll actually prove that your code meets the specs. And it's powerful, it does a lot of great things, but it will, as we can come back and talk about later, I predict, and I'm willing to bet money on this, that in 2 years, finding proofs for code meeting its specs is going to be dramatically automated compared to what it is now, using LLMs and other tech. So that's my sort of long answer to your question. We want to build on this, but I think everybody who works in machine learning can give a huge gift to people in cybersecurity by actually deploying LLMs to find these proofs. So what's a provably safe system, and what are we trying to do here? A provably safe system is just a system that you can prove that it meets certain formal specifications. You might want to prove, for example, that an airplane is never going to fly into a building even if the pilot tells it to. Right? Or you might want to prove that a car is never going to accelerate into a pedestrian even if the driver wants it to. Or you might want to prove that a piece of software is going to meet certain specifications, like in cybersecurity, like you can't log into this computer without having the right password. So provably safe systems can be either hardware or they can be software, or some combination, or even social situations and for governance. Provably compliant hardware is a special case of that, where it is hardware, like the example that I mentioned. You can imagine also that a GPU, you might be able to want to prove that it's never going to run certain kinds of malicious code, or that a DNA synthesizer that George Church has in his lab is never going to print out the smallpox virus or something like that. Proof, when it's software that's provably compliant, there's an extra cool feature that you can have, in addition to being able to prove that it respects certain properties, which is you can actually store the proof itself just as part of the software. So if it's queried, hey, give me your specifications and give me the proof that you meet them, it can give you the proof. It can just be, that can have been pre-computed earlier, and it just reports that to any operating system that wants to know it. That's called proof carrying code. And it's kind of like a virus checker in reverse. So raise your hand if you have a virus checker on your computer. So what it does is, if it can prove that your software is malicious, it will not run it. Otherwise, it will run it. Proof-carrying code is the opposite. If your code can prove to the operating system that it meets the specs the operating system requires, it will run it. Otherwise, sorry, I'm not going to run it. So in one case, for the virus checker, you're innocent until proven guilty. With PCC, you're guilty until proven innocent. It's the higher bar. And you can obviously have a hierarchy of provably compliant systems with hardware and software, etc., where if you have some GPU cloud somewhere which is only going to run software that meets certain specs, right? Now, it will check, it will ask all the software that runs there to prove that it's going to meet the specs. If it can't, doesn't, etc. You can go all the way down to the hardware level. You can even have it within individual pieces of code, like this function or this subroutine has to show that it's going to meet certain specs. And it's an old, the proof-carrying code idea is quite old for coming from the cybersecurity field, but I'm arguing here that not only is it ripe for a revolution and that it's going to become much cheaper and possible to produce this for much more complicated pieces of code, software and hardware, but also that we really, really need it. Why do we really need it? Because if we're dealing with systems that are much more intelligent than us, the only way we can guarantee that they're going to do what we want is if we can prove it. Right? No matter how smart the thing is, it can never do what is provably impossible. That's sink in a little bit, right? No, even if it's a super intelligence, it still cannot do something which is provably impossible. And you might also think, well, this is just hopeless, because how are you ever going to understand some super long proof about some very powerful system if we're just a human? The good news is, you don't need to. You just have to understand the proof checker. There's a famous proof checker in Python that's only 300 lines long in the MetaMath system, which you can read yourself. And it just checks, yeah, you substitute this into this, and this follows, etc. You just have to trust that, and you can run it on some super long proof written by some super complicated AI. You don't have to understand how it came up with the proof, but your software can quickly verify the proof is real. And another way to say this is it's much, much harder to discover a proof than to check that it's correct, right? In fact, the most famous theorems that you learn in math class, you don't know exactly how the person came up with them. Maybe they were in the bathtub or whatever, but you don't care. You can check that it's correct, right? So in principle, you could delegate to some very advanced AI system to come up with proofs about some other AI system. Once the proof is found, some little 300-line code on your phone or whatever, you can verify it. That proof checks out. So that's the basic vision of what a provably safe system is and why it's good. Now, before I get into the nerdy part here, which I want to dwell on for a little bit, I just want to say, you might be concerned, it's hard to even write the specifications for very powerful AI. Like, how do you write the specification that this thing is not allowed to kill any Harvard students or whatever? But let's not be perfectly the enemy of good. Even in the immediate term, there are some core things which are super easy to specify, like nobody should be able to log into your laptop without the correct password, right? Which we do not have formal verification for right now. Let's start with some of these tasks. People will love you for it if you figure that out, right? And then gradually we can up our game and trying to specify more and more complicated things. So there are so many things in cybersecurity. People are trying to formally verify Ethereum right now. Ethereum 2 still haven't finished. Critical infrastructure, so many things there that would be just great to be able to check, etc., etc. And so let's get a bit nerdy now. So how do you build provably safe systems? Let's start with software. How do you make software that provably meets its specs? Well, you can split it into 4 steps. First, you have to somehow discover the required algorithms and knowledge that are going to go into it, right? Then you have to create the spec that define what you mean by success, what you want. Then you have to generate code which meets the spec, and then finally you have to generate a proof that it meets the spec. The first part we've traditionally done, let's go through them in a little bit of a different order. The part about finding the proof, we already talked a bit about how there are a lot of nice tools for it, and I'm predicting a revolution. We can talk more about the details of that if you ask me in the Q&A. Generating the spec is something that we always want to remain something that humans do, right? We're supposed to build these machines for us, so we should specify what we want them to do. Now, in terms of discovering the algorithms and knowledge, and then generating code that meets them, traditionally this was all done by people. Someone came up with Cooley and Tukey invented the fast Fourier transform, and then they wrote the code, right? There are two other ways that you could do this as well. One is the field of program synthesis, where you try to train AI to actually write code. You can ask GPT-4, write me a code that does blah, 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 and it's pretty good at it. Today, it's kind of limited to writing software on topics which it's seen something similar, where it's seen similar things on the internet, but it's read all of GitHub, right? So it's probably not going to be able to invent entirely new algorithms yet, et cetera, et cetera. And then finally, there's a method based on mechanistic interpretability. So if you train a neural network, like GPT-4, it will often discover new algorithms that no human had thought about before. Like, it figured out how to translate English into Chinese real good, by itself. We still don't know exactly how it's doing it, but it's doing it better than anything we can code up, right? So wouldn't it be cool if we could have some automated technique where we first train a neural network to actually discover new algorithms and knowledge, and then automatically extract that out and turn it into code? This is the vision I want to spend the rest of my time up here geeking out on. It's very small. It starts with mechanistic interpretability, the quest to just understand more clearly how a neural network works. It's a tiny field, but it's growing really fast. You can see how tiny it is if I tell you that this is the largest conference ever in the field. It's so tiny compared to something like neuroscience, where you try to figure out how these neural networks work. And yet, this tiny field has already accomplished more successes, I would say, in the last year than all of regular neuroscience has, for reasons you can ask me about afterwards. But in short, in regular neuroscience, you struggle to measure what all your neurons are doing. Maybe you can measure 1,000 at a time or something, but you'd like to know all 10 to the 11 of them and all the 10 to the 14 synapses, right? So good luck with that. We still don't have that tech. Whereas if you're doing it, like people like Boaz Barak are doing, right, in a computer, you can just see what every neuron is doing all the time, and all the connections and everything. And you don't need IRB approval or anything like this. So this field has a lot of reasons for why you should expect it to progress faster than regular neuroscience. At the conference site here, Tegmark.org/MI 2023, you can watch all of the videos, and I think you'll be blown away by just how much success people have had, even very recently. There's been a lot of progress, for example, figuring out how large language models store facts about whether the Eiffel Tower is in Rome or Paris, and how you can edit the weights so that it thinks something else, and how knowledge is represented more broadly inside of neural networks. For example, here is a little toy example we did in my MIT group, where we just took an algorithmic task, it's generalized multiplication, which you have some sort of group operation, and you want to learn a bunch of examples that are held. You give it some examples, and then you see if it can generalize and predict the held out examples. If somehow the algorithm discovers some structure in this, that, oh, maybe this operation is commutative, then it can generalize, knows that the lower half is the mirror image of the upper half, and actually predict stuff you didn't tell it, right? If it discovers something else, like maybe this is an associative operation, it can generalize even better. And an interesting thing we noticed when we were studying what happens under the hood, for examples like this, Here we're just doing addition modulo 59, or abstract symbols. In the beginning, it just represents each symbol in some random way. And then suddenly, at the very instant when it learns to generalize, the neural network has this eureka moment where its representation crystallizes into some geometric pattern. In this case, it discovered that if it represents all these numbers, or putting them in a circle, it can really crush this task. I see a clock there with 12 numbers arranged in a circle. That's a very natural way to represent addition modulo 12. And what's clever about this representation, if you're just adding angles, is it naturally gives you the commutativity and associativity, which lets it generalize. So this is a very general phenomenon that a lot of people have seen now, many examples of it. If you look inside of a neural network, not only does it come up with algorithms, but it often comes up with very clever representations of the knowledge that make the computation simpler and capture key structure about it. So how can you complete the vision I'm outlining here? Take mechanistic interpretability, automate it completely so you don't need any human to do anything, and then actually take this kind of insights that are in there and automatically extract them out and turn them into code that you can then try to prove. To make this seem less pie in the sky, let me just show you a worked example end to end where we managed to get this completely automated. So this is an algorithm. So what we want to do is take some input data. Maybe you want to predict the last column of the spreadsheet from the previous columns. Train some black box neural network to nail this task. So now the algorithm is in here, but you don't know what the algorithm is. And then come up with some automatic algorithm distillation technique, which will just do something with this and turn it into proof-carrying code. Okay? How on earth would we do this? So let's look at an example of an algorithm I think most of you learned in first grade. Addition with the so-called ripple add method, where you first you loop from right to left. You start with a digit from each of the two numbers. You get this one output digit, and maybe you have a carry, or maybe you don't, and then you loop over to the left, right? Let's do this in binary. It's exactly analogous, and see if we can machine learn this. So we're going to focus now on seeing if you can get a black box to just master this task. We got it to work with a very simple recurrent neural network. Raise your hand if you know what a recurrent neural network is. So don't worry about the technical details otherwise. So basically, you send in a couple of digits at a time, one from each of the numbers, and then it outputs one output bit here at the top. There's a hidden state, which keeps getting updated at every iteration of this thing. And the whole neural network is just defined by these three matrices here that are shown in blue. So you train on your laptop in about 1 minute, it's nailed the task. And we managed to get it to work. The simplest version we got it to work with was with only 2 dimensions in the hidden space, which means that the internal representation of this thing can be viewed just as a point in 2D. And when we ran through all the training data, it was a complete mess initially when we started training. But after training, remember before how those things were represented in a circle? Here's something similar happened. At the point when it started nailing it, this all collapsed into 4 clusters. And it turns out that there were only 4 internal states. The whole thing became a finite state machine, even though it started out with continuous variables. With only 4 states. Moreover, if you look at this, so that you see this is a parallelogram, actually, these 4 points, which means you can think of it as this 4-state system as 2 bits. 1 bit corresponds to where you are along the red direction, 1 where you are along the blue arrow, right? So there's just 2 bits sitting in here. And that means we can actually just throw away all the continuous neural network and just ask what kind of finite state machine is this? How does the output bit get determined by whatever the 2 bits are in here, for example? So here's the table. Turns out that the output bit is actually just the first of the 2 bits that's sitting here. what about the more interesting thing? How is it doing this nonlinear update rule? What is this function here? It depends on 4 bits, the 2 input bits and the 2 hidden bits. The first bit was just the output bit. The second bit, it turns out, we stare at it, it's the carry bit that's discovered. What is that function? Well, automatically, of course, we can look at that, have the computer look at those 4 plots and what maps to what. You get this table for each of the 16 inputs, and here's what happened. I just wrote a little Python code to find the shortest Python expression that just is that function. And it turns out that the output bit is simply B XOR C XOR D, which is just, it adds up the 2 input bits and the carry bit, and outputs 0 if it's even and 1 if it's odd, right? That's what you do if you're adding in binary. And this is how it updates the carry bit. It takes the 2 input bits and the previous carry bit and checks if it's more than 1 or not. The neat thing about this is it runs end-to-end with no human intervention. I made these plots and started talking, rambling about carry bits and stuff just to give you a bit of intuition, but that was not necessary. It automatically output, in the end, this Python code, where, in particular, the stuff that's in red here was all just what it had to learn from looking at those neural networks with some automated techniques. And to go to the final step and prove things that this is actually always going to get the right answer, you can convert the Python into Daphne, this language I was plugging, which is very, very similar, and to Python. And then you have to just add a little bit of stuff. You have to add the Daphne command, ensures, for example, where you specify formally what is it that this function is supposed to do. I defined a little helper function called string to integer there, where it calculates from a bit string, what is the actual corresponding integer, and it's just saying that you want it to actually interpret these 2 as integers and sum them up. And then in Daphne, in some cases, you have to also add a few other statements, give it a little bit of hints or whatnot, and then it can prove that this actually works. So I want to leave plenty of time for discussion. So let me just wrap up by commenting on, is this hopeless? Again, this is very much the question that I touched upon already. Right now, this is obviously a small toy example, right? But this already shows you that the set of tasks that can be done end-to-end like this, where you just give it the data and it crunches on it for a while and then outputs a provable Python code, provable Daphne code, is not the empty set, right? It can be done. Clearly you can do a lot more. And what I'm predicting is that once we start using LLMs at a massive scale to aid the formal verification, we're going to be able to greatly expand the set of things that we can formally verify. I think we can go far beyond things like preventing people from hacking your laptop. Last, so if you're interested in collaborating with us, we have a really friendly group down the road at MIT where this is what we're really focusing on, very big time. And we welcome collaborators. This is a super fun set of problems. So much cool stuff to do. My email is just tegmark@mit.edu. Just reach out to me. I'd love to talk, or come grab me after this, and we'll talk more. Thank you so much.
If you can create your verified, safe, aligned AGI, are you worried that you also somehow have to make sure no one else in the world creates an AGI that isn't aligned and verified? And how do you deal with getting everyone on board in every country in the world that has resources to do so, and all private actors? Is it?
That's a great question. First of all, the way it is right now, right? There are no restrictions on what you can run in a large cloud, right? So anyone can do anything. So if some malicious actor for some reason wants to figure out how to make a new pandemic or whatever and run some new biosynthesis software, whatever, they can just do it. Whereas there are actually quite few manufacturers of the hardware we run on, like NVIDIA, for example. So what you can imagine is a situation where NVIDIA puts in their future GPUs, they make them into this kind of provably compliant hardware, and then if the US government, for example, wants to have, insist on certain kind of specifications that nobody can print out smallpox or whatever, right? That can be on the list that then you won't be, if nobody can run it on NVIDIA chips, the set of malicious actors who can make their own GPUs is much smaller than the set of people who can just write the code. And second, if you look globally, you might think, oh, different countries can never agree really on anything or whatever, but that's obviously not true, right? US, China, Europe, Russia, whatever, they've all signed on to the Sustainable Development Goals. None of these governments wants to be overthrown by one of their own tech companies who does something crazy or starts a pandemic. That's where you're seeing in parallel a lot of efforts to try to create regulation all over the world. So if you start with some basic stuff like airplanes shouldn't be able to fly into buildings, nobody should be able to hack your SSH, I could easily see policymakers around the world being quite enthusiastic about having this in their toolkit, where they can start saying, hey, NVIDIA, whatever, all the companies that sell GPUs, they have to support this kind of a feature. It's not exactly new. We do it in other tech already, in biotech, for example, where companies aren't allowed to just invent a new medicine and start selling it in Walgreens. They have to do clinical trials. There are all sorts of situations where you have to prove that things are safe in various ways. And this is basically just adding that sort of technical base layer that gives policymakers these kind of abilities. Yes, right here.
Do you see the policies coming from humans still, or will they be used as LLM generated in the future?
So this is now not a question about what will happen, but what ought to happen. So I'll just tell you my personal opinion. My personal opinion is that we should only build these sort of technologies if they're going to be good for us humans. And I would like it to be us humans, therefore, who decide what they're going to be used for. Sometimes people say, oh, let's just build some really smart machines and have them decide the policies. That's sort of a cop-out, because as if there's only one way a smart machine could choose to do things, right? You can have virtually any values built into a machine. Intelligence is not the same thing as having high moral standards. Like if Hitler had been more intelligent, do you think the world would have been a better place or a worse place? I think it would have been a worse place, right? So I really think, I would like to see us humans own up to this, step up to this responsibility and ask ourselves, so what kind of values do we want? What kind of future do we want? And then make sure that that's what we make our machines do by these sort of approaches. Try to be democratic between left and right, yes?
Okay, how do we ensure the system is safe over an entire real-world event distribution? Do you have to explicitly specify disallowed operations? And if not, why can't a misaligned agent just masquerade as good for what you test and then act badly afterward?
Here you're highlighting the very important difference between what people casually call aligned and what I'm calling provably safe. So if you, let's compare this with debugging. Debugging is a great way to make your software more reliable, but no amount of debugging is going to prove ever that your software is correct. It can only prove that it's incorrect, and if you fail to prove that it's incorrect for a long time, you're like, it's probably fine. I'll deploy this. The only way you can prove that it's going to work for all inputs is with an actual mathematical proof. And that's where formal verification shines, because it can actually prove things about infinitely many potentially arbitrary or these massive input spaces. I don't think it's feasible to take something like GPT-4 and prove a lot of interesting theorems about it, because it's an architecture that's very messy and doesn't really lend itself well to mathematical proofs. That's why I'm more optimistic about this idea where you let the neural network figure out the algorithm. And then after that, you throw away the neural network and re-implement it. I just want to add, because this leads to something that's very, very important that I think is often overlooked. We all love neural networks. They're so great, right? But why are they so great? What are they so great at? There are two quite separate tasks, the learning and the execution. I'm arguing that in terms of execution, like in runtime when you go to GPT-4 type stuff, neural networks are not particularly great. There are many massively parallel systems that can execute code, even on GPUs. Neural networks are one of them, and they're about as good as other ones. Where neural networks really shine is not in execution at runtime, it's in learning. Because they relax the problem into this continuous space where you can use gradients always to figure out which direction you should go to get something better. Good luck doing that with a Python code to change a random letter and see if it got better or worse. You're just going to get syntax errors, right? It's the learning where they really shine. So my vision is let's use neural networks for what they really rock at, the learning. But with the idea that if it's some kind of safety critical application, we don't need to deploy the neural network. We take out the algorithm and deploy it. It's a lot like what we already do with our own brains. You know, if you want to send a rocket to the moon, you use your own brain to figure out the laws of gravity and all that stuff. But you don't put your brain in charge of steering the rocket in real time. You extract out the algorithm from the brain of all these physicists, you code it up into some software you can verify, and then you send that to the moon. Okay, let's see. Trying to go democratically around here. Yes, in the green shirt.
Oh, me?
Yeah.
I'm curious, like, extracting the algorithm from the model seems really, really hard.
Yes.
And I'm curious, like, how do we need to solve, like, the superposition problem and stuff like that before we can do approaches like this, or how are you thinking about this?
We need to make a lot of progress, yeah. In this case, we didn't bump into superposition.
Yeah.
There are many different algorithms also for adding numbers. The one that we discovered it was doing is the ripple add that we all learned in first grade. But I bet if you ran it many times, there was something to discover other ones. But yeah, for more complicated ones, there are clearly going to be a lot of fun challenges to overcome here. You should think of this as an existence proof. There are already algorithms where we can go completely end-to-end like this. But what we're building right now is a large benchmark of algorithms where we have a neural network that does something cool, and then we can give that to everybody, and they can try to beat us and see, can you get more, can you do it with 10%, can you get the algorithm out of 16%, 18%, friendly competition, MIT versus Harvard. It would be super cool if some of you can join us on this. And I think in the process, it's going to be a really exciting intellectual journey of discovery also, because there's just so many beautiful ideas involved in finding the patterns that it's discovered, that it's not just going to, it's going to be a lot of fun also. It's challenging, but lots of fun, I think very doable. And we can use machine learning also for those tasks. And one last thing, superposition and things. You might find also, so one of the techniques we use a lot is if the algorithm is in there in a very messy way, sometimes you can give the neural network extra resources and then use a bunch of regularizers and it'll come up with a simpler way of doing the same thing, which is inefficient if you were actually going to run that thing at runtime. But all we're going to do is throw the neural network in the garbage anyway. So we just want to regularize the neural network until it does it in a simpler way, maybe without superposition, figure out what it's doing, and then bye-bye neural network. Okay, yes.
So you've intentionally constructed a toy model here that has like a highly compressible algorithm,
yeah,
in the sense that the algorithm that the neural network learns can be specified in like much fewer operations than are actually used when the neural network executes a forward pass. I'm not actually convinced this is true in general for large neural networks. Like if you have a diffusion model that's generating images in a continuous output space, I don't know that you can like write down what that neural network is doing with pseudocode that's much simpler than the network itself.
Yeah, you have to be very open to the possibility it might be this way. For the particular case of diffusion models, we had a paper recently where we found this other diffusion model based on the Poisson equation where you can actually understand with a short algorithm how to get stuff even straight from just your training data, and you don't need, but it could be. It could also be though that, so if you think of a Venn diagram, like this is the class of what we can do today, so almost nothing, right? And
There's some markers over there.
oh, perfect, then I don't have to draw with blood. So we can do this today, some little toy algorithms, okay? These are like all the algorithms we can do now. Here is all the algorithms we'll be able to do with machine learning in 2 years. And how big is this set of algorithms that we'll be able to extract and prove things about in 2 years? I don't know, maybe it's like this. It might not be the whole thing, but it's a very interesting question to ask. Does this still contain a lot of super useful things? And as long as the answer is yes, then you're clearly going to want to deploy that technology, right? In particular, it might well be that for a lot of very high stakes things like operating the power grid and whatnot, there might be smaller algorithms. In fact, one of the main emotional takeaways I had from the Mech conference, watching talk after talk after talk, was that whenever people figured out how some neural network was doing something, I was like, oh my God, that's so stupid. This would be more efficient like this. Like it's storing things in a matrix linearly by having row vector, like if it just stored it in the database, it would be more efficient. Or so it seems like the neural networks we train are not incentivized normally to do it the clever way, right? So it might very well be that a lot of the stuff can be done a lot simpler. Yeah.
Can I just briefly point out that some of that might be selection bias, where if you can't distill the algorithm into something easily understandable, then obviously you're not going to present a paper on it. So people are only finding the algorithms that they can easily describe.
I try to be very humble about this. We honestly don't know. I do feel the best way to find out is to try. The best way to fail is to say, it's probably impossible, so I'm not going to work.
Maybe a related question is, the paradigm you're suggesting here is in some sense to extract an algorithm from the network and prove that it matches a specification.
Yes.
And in some sense you would like a simple specification, one that humans are able to say specify and then check correctness against that. Where maybe the paradigm that would scale up would be to have a very complex algorithm, but have a partial specification. Because, for example, if you take something like, say, Microsoft Excel, I don't think we can even write a specification for what Microsoft Excel is supposed to do, but maybe we can have some properties that it should never add up numbers incorrectly or some other properties.
Which would have saved Intel a lot of money when they had the famous Pentium bug, if you probably remember.
Yes, so maybe what we need to do is to think about very complex algorithms, but prove partial specifications.
I agree. And if you think about every program you ever wrote, it probably has subroutines and functions in it, right? All sorts of modules. So it makes a great deal of sense to separately verify the different modules also, and then you can mix and match, build from verified parts. This is also something you'd like to do with hardware later when you build complicated systems like, this heat sensor here is verified, and this sensor is verified, and this code is verified, and now you put them together. You don't have to go back and prove something super complicated from scratch. But instead you're building on a strong foundation. Yes, Lukash.
Do you see provability being used during training rather than at runtime?
So you can also generalize this to probabilistic reasoning. We talked about that in our paper. Then what you'd want to do is sort of epsilon delta proofs and say that this algorithm here will, under these circumstances, these assumptions will fail with a probability smaller than 10 to minus 100 or whatever, and then you, the user or the regulator, can decide kind of where you want to set the bar. That's what the FDA does when they approve drugs also, right? They're not insisting that the side effects should be zero. but they want to have some kind of bounds on what they are. Okay, all the way in the back there.
Minutes left, so maybe 1 or 2 more questions.
Okay, yeah. Do you want to decide who's the lucky one? The lucky ones are, so I don't feel guilty. Okay, white shirt.
Yeah, to kind of build upon what you said before about specification, I was wondering, like in the realm of AGI, like once we actually get to AGI, you would probably need full specification, no? Because you need a system that's gonna probably recursively improve and that's gonna be deployed virtually everywhere. You would need full specification by then. And I was just thinking about like Asimov and his laws of robotics and how he tried to have, I mean, he showed how many examples you could like easily find a system which like goes away from those laws. Do you believe that it's possible to have full specification before we reach AGI, and like how would that come about?
I'm quite confident there were a lot of things we can formally specify which would be already very useful that we should do. For example, one of the first people who was killed by a robot it was not because the robot turned evil or anything like that. He was standing in a place where the robot arm was told could never go, but the robot arm went there and crushed him to death. And you know, it's just a trigonometry problem. You cosine this, sine that angle to figure out where the robot arm is, right? You can just write down an inequality saying the robot arm can never have an x-coordinate bigger than 5 meters or whatever, right? And that can be part of the specification. These are the sort of things which industrial engineers would love. If you think of more powerful systems in general, I would love to have a formal specification that this machine will always let you turn it off if you want to, if you're the authorized person. This is a famous, quite difficult problem called the corrigibility problem, right? Not hard to specify. So before losing a lot of sleep about how you're going to specify that it's going to make all Harvard students happy or something fluffy like that, I would encourage you all to think about what are the most easy to specify things that would already be a good step forward, and particularly focus on things which remain relevant even as you get to AGI and beyond. Okay, the last question is going to be selected by lottery. Somebody shouts stop. Stop. You got one already, right? So I think I'm going to go you. Yes.
Can you say a few words on like what you think the major roadblocks you see for mechanistic interpretability and the state of progress?
Yes, I think that the main thing that's limiting it now is there's so few people working on it still. And this is an incredibly tiny conference for being something computer science related. So part of my talking to you about this is also just hope to persuade more people to work on it. It's a super fun field. I think that's really the main one at this stage. There are a number of. Chris Ola gave a very nice keynote speech at the conference where he outlined what he viewed as all the technical roadblocks right now, and one of them called superposition even came up. You can check that out for more deets or corner me right after here. But there's nothing I've seen which suggests to me that the field is going to come to screeching halt anytime soon. So I'm optimistic. Well, good. Thank you so much again for inviting me here. It's such a pleasure.
I thought 50, this is more like 120. But yeah, as a reminder, if you're interested in talking more about neural network interpretability or, I don't know, listening to knowledge, and stuff like that, go to haste.ai. And I don't know, Max Tegmark, do you want to stick around for a few minutes?
Yeah, if anyone else has more questions you didn't get in, I'll be